Okay, now for example number 4, we want to find the length of one arch of the cycloid, where x is equal to r times theta minus sine theta, and y is equal to r times 1 minus the cosine of theta. Now back in example 7 in section 1.7, we would see that one arch is described by the parameter that theta would be in between 0 and 2 pi inclusive. Since dx over d theta is equal to r times 1 minus the cosine theta, and dy over d theta is equal to r times the sine of theta. Now using our formula number 1 going from 0 to 2 pi, the square root of dx with respect to d theta squared plus dy with respect to d theta squared d theta. So going from the lower limit of 0 to 2 pi, we would square the derivative of x with respect to theta, so we would get r squared times 1 minus the cosine of theta squared plus r squared times the sine squared theta d theta. Then what we can do is then we can go ahead and then multiply this perfect square trinomial. We would get 1 minus 2 times the cosine of theta plus cosine squared theta. And since they both have r squared as factors, we can factor that out. We have plus sine squared theta d theta. So we know that cosine squared theta plus sine squared theta is 1. So that becomes 1 plus 1, which is 2 minus 2 cosine of theta. And so we can factor out the 2, and we can also factor out the square root of r squared, which is r, and apply that as a constant outside the integral. So we would get the square root of 2 times parentheses 1 minus the cosine of theta d theta. And this integral could be evaluated after using further trigonometric identities. Instead, we're using a computer algebraic system, and we would get 8r for our solution. So the result of this example says that the length of one arch of a cycloid is 8 times the radius of the generating circle, which is what you see in this figure. This was first proved in 1658 by Sir Christopher Wren, who later became the architect of St. Paul's Cathedral in London.